This is the first in a series of resources that consider the four different types of sequences. Part 1 defines sequences and also considers sequences defined by a general rule. Part 2 inspects arithmetic sequences, the general idea, how to find specific terms in the sequence, and how to find a partial sum of the sequence. Part 3 looks at geometric sequences, the general idea, how to find specific terms in the sequence, how to find a partial sum of the sequence, and also how to find the finite sum of an infinite series. Part 4 considers recursive sequences. We will look at the basic rules and formulas, then work through examples of each. A sequence is a special type of function. In official mathematics language, it is a function whose domain is the set of all positive integers. In more normal language, a sequence is a list of numbers, where the integer input represents the position in line. For notation, we use the variable a with a number subscript to represent each value in the sequence. We will have a sub 1, a sub 2, a sub 3, all the way to a sub n, and on. A quick note about using subscripts in mathematics. They have no operational meaning. We do not have any math to do with the subscript. It is only a counter. So a sub 5 means to find the number that is the fifth in the list. But how do we actually find these numbers in the list? Well, it depends on the type of sequence. There are actually four different types of sequences, defined by the method for finding the numbers in the list. The four types of sequences are general, arithmetic, geometric, and recursive. We will focus on the general sequence in this resource. The most basic type of sequence is when the elements in the sequence are defined by some function in terms of n. So to find the number in a given numbered position, we just need to plug that number into the function and solve. These functions can be as simple or as complicated as we want. Let's look at a couple of examples. Suppose we want to find the first four numbers in the sequence where the general term a sub n is defined by the function 2 multiplied by n plus 5. So to find a sub 1, we plug in 1 for n. We have 2 multiplied by 1 plus 5. This gives us a sub 1 equal to 7. A sub 2 is then 2 multiplied by 2 plus 5. A sub 2 equals 9. To find a sub 3, we multiply 2 by 3 and add 5, giving us a sub 3 equal to 11. Finally, a sub 4 is 2 multiplied by 4 plus 5, which equals 13. But what if the function is more complicated? What if we want to find the first three terms of the sequence where the general term a sub n is defined as -1 raised to the nth power divided by the quantity 2 raised to the nth plus 1? And just for giggles, what is the ninth term of this sequence? To find a sub 1, we plug in 1 any place we saw n in the original definition. We have -1 raised to the first power divided by the quantity 2 to the first plus 1. -1 to the first is -1. 2 to the first is 2. Combining in the denominator, we find that a sub 1 is -1/3. For a sub 2, we have negative 1 squared divided by the quantity 2 squared plus 1. Negative 1 squared is 1, 2 squared is 4. Simplifying, a sub 2 is 1/5. Looking for a sub 3, we take negative 1 raised to the third power divided by the quantity 2 to the third plus 1. Negative 1 to the third is negative 1. 2 to the third is 8. Finishing, a sub 3 is negative 1/9. Our last task is to find a sub 9. To do so, we have negative 1 raised to the power of 9 divided by the quantity 2 to the 9th plus 1. Negative 1 to the 9th power is negative 1. 2 to the 9th is 512. Combining in the denominator, we find that a sub 9 is negative 1 over 513.